This is a review for the Unit 3 test. Just a quick review of a few things, not everything on the test, that I thought people would have questions about. So, how to get ready first for the Unit 3 test. You should go through all of your notes and the problems in the packets, the notes packet. Last test we had questions straight out of there. Look through them and make sure you actually understand the questions. And if they were worded in a different way or had a different compound, that you could answer them. Go over your owls from this unit. We had 3 owls. Go back over those. You can redo the owls again and again, but those have good questions in there. Look at the progress check questions. Now remember, not every question on the progress check will be on our test. There's a few things like PES. We haven't done molarity. We're doing next unit, but we can't change the progress checks from AP Classroom. But the ones about topics we did do those. I assigned you videos on AP Classroom. Watch those. Those are good. And then go back over the 2 labs that we did. There will be a question over each lab. Okay. So first, we haven't done Maxwell-Boltzmann distributions in a minute. So this is a distribution of gas particles. Now really fast. Remember that kinetic energy, and you do get this equation. The equation is 1/2 mv squared. M is mass, v is speed. And that temperature of something is a measure of the average kinetic energy. Now, it's an average kinetic energy. There are always particles. Let's say I've got something like this right here. I've got a mole of gas at 200 Kelvin. There are going to be some things that have a kinetic energy greater than whatever 200 Kelvin is equivalent to. And there are going to be some that have less. But the average should be around there. And so let's say this showed a mole of gas at 200 Kelvin. Also remember, the area under the curve tells us the total number of particles. So let's say I changed it and I said you were going to have 2 moles of gas at 200 Kelvin. Now, the area under the curve, the total number of particles, should double because the amount of particles doubled. And so you would just need to make it like, same. The peak should be at the same spot, but the space would be doubled because you doubled the amount of gas. Okay, and let's look at this one. And again, remember, x is speed, y is number of molecules. Let's say this was 1 mole of gas at 200 K, and I said I wanted you to draw 1 mole of gas at 300 K. Hold on one second. Hold on. Okay, sorry guys. Dr. Burrow came in. But let's say so this shows a mole of gas at 200 Kelvin. I want to show a mole of gas at 300 Kelvin. So temperature has gone up. Temp is up, which means it's going to shift to the right. But the area under the curve should still be the same because it's still a mole of gas. And when you shift things to the right, the peak won't be as high. The peak will be lower. And so it went a little bit higher. Now I don't have any speed markings on here. It doesn't really matter, but something like this would show it at 300 Kelvin. So our average speed is higher because the temperature is higher, and that area under the curve is probably the same. Again, these are guesses. They're not going to be like, I'm not pulling out a ruler to measure the area under the curve. And then let's do another one. Speed, number of molecules, and this time let's say I have a mole of H2, and this is H2 at 200 Kelvin. And then I wanted to know what it would look like if you had a mole of O2 at 200 Kelvin. Now to figure this out, so temperature is the same, which means average kinetic energy is the same. And if we think about our equation, Ke equals 1/2 mv squared, so this number is staying the same. But what has changed? It was hydrogen, now it's oxygen. What do we know about the mass of oxygen? We know oxygen weighs a lot more than hydrogen, so mass has gone up, which means if temperature, or average kinetic energy, is going to stay the same. There you go, you can see that now. That velocity, if this number is going to stay the same, but mass has gone up, then the average speed or velocity has to go down to keep it the same. And so that would, if speed is going down, that's going to shift our x-axis to the left. Now, when it shifts to the left, we still have a mole of gas, so the area under the curve has to still be the same, but now it's going to be shifted left, and it would look opposite of this one. So when you shift left, the peak should be higher, something like that, because we need area under the curve to still be the same. And so this would show that velocity has gone down, and velocity went down because the mass of the gas went up. Also, with gases, we talked about effusion and diffusion. So gases with a larger molar mass, they won't effuse as fast as something with a smaller molar mass. So let's say, and there was an example in your packet that had a tube. So let's do that again. And we've got hydrogen and oxygen. And I want to know which one's going to travel further. Hydrogen would travel further in the same amount of time because it's smaller. Or if it was going like through a pinhole, diffusing through a pinhole, more hydrogen could diffuse through a pinhole than oxygen because they're smaller molecules. Those gas particles are very tiny compared to oxygen, much bigger. Okay. And then deviations of the ideal gas law. So you should know your 5 postulates of the ideal gas law. And basically with the deviation questions, you have to reason through them. And that's that quiz we did on Monday, reason through the answer choices. And really what it comes, deviations from the ideal gas law, what they come down to is the volume of gas particles can become significant. Kinetic molecular theory says you ignore the volume of the individual gas particles because the space is so big, their volume doesn't matter. That's not the case anymore. And normally this happens at high pressures, because if it's at a really high pressure, then the volume is probably really small. If the pressure is going to be that big. And so if we're talking about a tiny space, now those gas particles, their volume is taking up a good chunk of the volume of that container. And so that is one way that will cause the calculations from the ideal gas law to be off. It won't be correct at high pressures for volume because that ignores the volume of the gas particles, and gas particles have volume. And then also, gas particles, real gases, do have intermolecular forces between the molecules. So like, let me think of a gas. Even carbon dioxide. Here, doesn't really matter. So CO2 is nonpolar and will have London dispersion forces, which are still attractive forces between one another. In ideal situations, there is no attractive force between these two CO2 molecules. But in unideal situations, which is low temps and high pressure, they can have London dispersion forces between them. And when that occurs, now they're attracted to one another. That slows them down just a little bit more, and now they're not going to collide because they're attracted, and now they're not going to collide with the walls as much, which will change the pressure value from what the ideal gas law says it should be. Because they're attracted, they're not going to hit us with as much force because they're being attracted to one another. And they're not just flying around free. Polarity and IMFs. You should have an idea that IMFs are going to be a big chunk of our test. Particularly London dispersion forces, dipole-dipole, and hydrogen bonding. We spent a lot of time on these, and they kind of explain everything. They are going to be a good chunk of our test. So you should know what those forces are, what makes them stronger, weaker, and what type of molecules have them in between. And when it comes to IMFs, I think one of the biggest things where people mess up is you need to draw the picture, or if you're given a picture, really look at the picture. And remember, positive and negative charges attract one another. So like water. Water looks like this. Choo-choo, choo-choo. And the oxygen is the partial negative. The hydrogen is the partial positive. If I have something else polar, like NH3, we saw that one a lot. NH3 is a polar molecule, nitrogen is the partial negative, hydrogen is the partial positive. The intermolecular force, the hydrogen bond in the case of this one, will occur between the H and this N, because the partial positive will attract the partial negative. And then that would be a hydrogen bond. So positive, negative attract. Draw your pictures. And then remember, with hydrogen bonding, you have to have an OH, an NH, or an FH, and then the H has to be by an F, an N, or an O. So NOF is the key. If you have NH3, like let's say I have this molecule right here, and it is by CCl4. Now let's do that. Let's do that thingy. So now that thingy is polar, chlorine would be a partial negative. Hydrogen is going to be partial positive. And yeah. And so where's it going with this? Oh yeah, the chlorine and the hydrogen would be attracted to one another, but that is not a hydrogen bond, because that is a chlorine. It's not an F, N, or O. And then vapor pressure. So vapor pressure has to do with intermolecular forces. So vapor pressure, if something has a high vapor pressure, that means they have a tendency to become a gas. And if we think about solids, liquids, gases, solids are very close together. So they have lots of intermolecular forces. Liquids are a little further apart. They still have intermolecular forces, but the particles have more kinetic energy and they move around a little bit more, but they still have intermolecular forces. And then to become a gas, and all of these are going to be about ideal gases, they are far apart and there is no intermolecular forces between them. And so if something has a tendency to become a gas, that means they have a tendency to break their IMFs. That means that they have weak IMFs. For example, water has hydrogen bonding. Hydrogen bonding is really strong. It requires a lot of energy to break those hydrogen bonds apart. And so water doesn't have a high vapor pressure under most temperatures, because that requires a lot of energy to break apart those hydrogen bonds. So high vapor pressure means weak IMFs. Weak IMFs means a low boiling point. And you might see some vapor pressure graphs. They all have like this general shape. You can tell the boiling point. Remember, boiling point is the temp at 1 atm, which is also 760 in mmHg. And so on these graphs, let's say that's going to be 1 atm. This is temp down here. That will tell you the boiling points, which then you can figure out, okay, lowest BP would be here. So these have the weakest IMFs compared to highest boiling point over here, the strongest IMFs, and the lowest vapor pressure. And then last but not least, phase diagrams, because you really have never seen these before. So phase diagrams you'll see like this. They're not going to be labeled, but they all have the same general label: solid, liquid, gas. And so this point right here, that is the triple point, where they're all all states of matter occur at the same time. We watched that video. And then this line right here, so this line tells us where it goes from a solid to a gas, or from a gas to a solid. So that shows the phase change. This line would be where it either melts, fusion, or freezes. And then this line would be where it vaporizes or condenses. And then on a phase diagram, let me just draw another one. At pressure, this is always pressure over here, 1 atm. This is always temp. You can figure out what temperature it will melt and boil at, which I drew a really bad graph. It normally wouldn't look like that. It's not going to be at the triple point, so ignore that. But 1 atm can tell you melting and boiling points. And then you can also figure out and that's typical melting and boiling points. So as pressure changes, what state of matter will it be and what temperature will it melt or boil at instead? And so let me draw a better one. Okay, so solid, liquid, gas, and this is 1 atm. So and I don't care what this is, let's just make up and pretend that is 40 degrees and that is 60 degrees. So normally this substance would melt at 1 atm and 40 degrees. And then it would vaporize or boil at 1 atm and 60 degrees Celsius. But let's say the pressure, let's say it's at 60 degrees and the pressure is 0.5 atm. What state of matter would it be? So this is pressure 1 atm, 0.5 is going to be down here, and so it would be a gas. It would not condense at, or sorry, it would be a gas at the lower pressure, even at the higher temperature. And so I wanted to know at 0.5 atm, could it even condense? And with the case of this one, if you look at 0.5 atm, it never goes to the liquid state of matter. This random curve I drew, yeah, you could only get it when pressure is 0.5 atm. It can be a gas or it can be a solid, but it can't ever be a liquid at that pressure. Carbon dioxide is like this. Minus carbon dioxide, 1 atm is like down here. And that's why if you have ever played with carbon dioxide, it goes from solid to gas. It is very hard to get it in the liquid state of matter. It has to be a high enough pressure and very certain temperatures. And so that's reading the phase diagram. Oh, and then critical point is right here at the end. So solid, liquid, gas, lines show us phase changes. Read your graph, triple point, critical point, and you will crush this test tomorrow.